Shall we start the session?
Yes. Sure.
Yeah. Let me give a brief introduction and I'll hand it over.
Please.
Thank you. Good afternoon, everyone. Welcome to Skill-Link's corporate webinar edition. This is the 10th edition of our corporate webinar series. For those of you engaging with us for the first time, we are an engineering upskilling platform focused on advanced engineering technologies across domains like mechanical, electrical, civil, telecom, etc. Our enterprise business focuses on employee training and upskilling across industries, including automotive, telecom, ER&D firms, IT, ITES, product and product engineering services. So today's webinar is on software-defined vehicles, and we have with us Mr. Jegan Amirthalingam. Mr. Jegan is the Associate Director and Domain Head of Embedded Systems at Skill-Lync. He is a Senior Corporate Educator with 12 plus years of experience, having worked across firms like RNTBCI, KPIT Technologies, TCS, etc. We are glad to host you all. Over to you, Mr. Jegan. Thank you so much.
Yeah, thank you. So welcome everyone in today's session. We'll talk about software-defined vehicle. This has been a buzzword in automotive from 2018. In this short webinar, let's try to understand what is this software-defined vehicle means. If you want to start yourself to upskill on software-defined vehicle, what are the key technologies that is involved, and going forward, what this software-defined vehicle will bring, or what kind of changes that this SDV will bring in the whole automotive ecosystem. These things we will discuss in the short session today. I welcome you all. Thanks for joining. Let's get started. So typically I'll start my session with asking this question: how many lines of code that there is in the typical vehicle software? Which means we have a large group of ECUs, a large number of ECUs connected via CAN, LIN, Ethernet networks inside your automotive. So putting this all together, what is the total size of your vehicle software? Any rough guess? You can put it on the chat so that I can able to see. Yeah, Gauri Shankar is telling 300 millions. Interesting. Vivek is telling a few 10 millions. Any other answers? At tens of few millions. Okay. 100 million. Okay. So earlier it used to be 100 million. Now we are moving ahead with 150 to 200 million lines of code. So here is a quick comparison. In a typical modern car, the number of lines of software, comparing it with the tools like bigger IT giants like Facebook, then your macOS, who are actually into software product development. So if you compare Apple's macOS X, it almost has 85 million lines of code. Whereas a typical high-end car software is 100 million lines of code. So going forward, the car OEM will act or will have or will produce or will integrate more number of or a bigger software than what a company like a typical software product company is doing. So there are some best practices that needs to be derived, adapted from those industry, and from there the term software development or software defined vehicle is something coined. So when you say a car maker or a car OEM is holding a software which is of 100 million lines of code, which is actually bigger than Mac OS X, then there is going to be a unique growth or a very, very bigger growth in the upcoming time. This is because by 2030 we are anticipating that there will be level 5 autonomous car. So this level 5 is the SAE level, which means you don't want to focus while the vehicle is driving. It's completely autonomous. You keep your minds away. So that's the level 5 autonomous car. It will be it might be eating around 2030. Let's assume. In that case, we will be having around 1 billion lines of code. So what this potentially means? So potentially it means all the OEMs who are involved in the vehicle software development, or who are involved in making a vehicle, especially when I say vehicle, let's take a light commercial vehicle, heavy commercial vehicle. There are many families of vehicle. Let's talk about a light commercial vehicle, which involves many bigger features like electrification, connected, autonomous, infotainment, all these things. So by 2030, these companies would have more, or would be building more software assets than anybody else. So that is what at that time, or we are moving towards that phase. That is why we are calling that whole product as software defined vehicle. And why this line of code is very important. So what this means to us, line of code is actually considered as one very important productivity metrics. When I say even in typical software company, they will use this metric to evaluate how productive a trained resource or a billable resource working in a project. And also, in what is the difference that we see in automotive industry is this: automotive industry is actually taking a shift very, very rapidly. That happened a decade ago in telecom industry or in mobile industry. So here now this era, I would say it's for automotive, where the kind of software complexity is actually increasing very, very rapidly. So we are not saying this; it's derived from a McKinsey report, where the software complexity in the previous decade itself, if you see, it has started growing exponentially. Now in the next upcoming decade, or in the current decade, we will be seeing the complexity level has been rapidly, very rapidly, or very exponentially growing. So if you compare the relative growth of the software complexity and productivity over time, when we say productivity, that includes how quickly we can able to solve the problem and how rapidly we adapt to that new technology. All this includes the productivity over time. So the productivity over time has been increased only from 1 to 1.5, whereas the complexity has been grown from 1 to 4. So this itself shows that there is a large gap between the kind of problem that we have to solve and where we are starting. Now let's talk a bit about what is software-defined vehicle. So a software-defined vehicle is very clear that separates the hardware from software. So this is the first definition. Like if you refer any of the existing literature of SDV, it says that in a vehicle where your software is completely separated from the hardware. I'll give you an example. When we say the software is completely separated, what do you mean by that? If you ask me, in the current market, we are using products like mobile phone, where there is a large ecosystem of Android app developers, iOS app developers. These members are developing an application software that's completely independent of the hardware, of the underlying hardware. Nobody is dependent on, nobody is building an application that runs only on a Samsung phone, that runs only on a LG phone, on this particular architecture, on this particular target platform. So these app developer community builds the app that runs typically on a runtime environment. So that's the first requirement, where the actual idea was to separate hardware completely from the software. And again, this software is updatable, upgradable, which means after delivery, after I'm packing and I'm delivering, even after that, there is a provision or there is a means to update it. So this updation, now it is inevitable, and we are seeing the result of that is the entire mobile phone market. So whenever we, as a user, we get a lot of flexibility as a device suppliers and as a software suppliers, they are evolving with new business model. So this, I would say, this upgradable feature is, if it is there completely defined in your vehicle, then it is called as software defined vehicle. Also, we require this sort of upgradable features when it comes to autonomous learning and always connected vehicle that interacts with its environment. And also it has to support a service-based business model. So in a short, if somebody is attempting to define SDV, the vehicle is completely driven by software, and that piece of software is completely isolated or like unplugged or dependent or independent of the hardware, which is updatable and upgradable. Now let's try to understand what is the current challenge that is existing in automotive industry. Always for automotive industry, they are integrators, and they need something called, or they need to satisfy, or they need to reduce the time to market before their rival bring any such product to the market. And always they like fight with, or they chase behind meeting all the standards. What if not, they can't able to bring their product to the market. It's reducing the product time, like time to market, time taken to bring a product to the market. This they will try to reduce. Second one, they completely try to chase behind the standards, meeting the standards. These are default challenges. Now, along with these challenges, the customer expectation is also very, very rapidly changing, where they were expecting some sort of user experience as they get in their mobile devices, because your vehicle is no more a mechanical system. It has turned, or it has evolved in such a way that it is completely an embedded mechatronic system, which offers certain autonomous features, which offers certain connected features. Just a minute. So one thing that is expected from the user community is the kind of experience that they expect from the mobile devices. Also, the car needs to provide a different levels of autonomous driving, which require a large data-driven based machine learning technology that is running. So if you take the autonomous software stack, be it perception, which is LiDAR, radar, signal processing, be it control, be it planning, at various stages of the software pipeline, certain machine learning model is running, which is running with which is built with a data-driven approach, which heavily relies on the data. And this model, if there is a provision to fine-tune, and there is a provision to evolve this model, that's very, very good. So again, this is a bigger challenge for many of the OEMs. Then environmental regulations such as climate change, that is leading to the electrified vehicles, and the regulations also vary from country to country. So once we deliver a product, it's like recalling the product and fine-tuning or flashing. So the big challenges in today's automotive industry lies in these four areas, which is autonomous, electrified, connected, and shared mobility. They simply call it as CAES, ACES, AECS. So with the different terms, but putting together, this is the challenge that is faced by OEM. So OEM, to save or to be self-sustaining in this market, they need to solve these kind of problems. If not, somebody would be taking over them. So these are, I would say, key motivation for SDV. So connected features are becoming mandatory in the cars. L4, L5 automated driving that we are talking, where the vehicle would be driven by AI models, and access to vehicle data. So large amount of data could be exchanged between a centralized cloud and the vehicle zonal ECU. Then there is going to be a strong integration between the service provider, OEM, and the final end users. So these are different, or these are acting as a motivation for a OEM to completely rethink into the SDV. So if you ask me whether this SDV is something that is completely new, or these kind of things have been evolved earlier, the answer is yes. They have this kind of software-defined things have been happening in other industries as well, or I would say happened in other industry as well. Just to give you an example, we have seen software-defined networks in telecom. Software-defined networks is something that separates the data plane and the control plane, which means you don't require a very large hardware for isolating, for bifurcating your applications. And so by introduction of this software-defined network, we can in fact handle very flexible application on top. So being it that you can handle the data also very wisely. So it provides a programmable, completely software controlled, without any big manual configuration or without any big interference of hardware. This has been achieved. Purely this has been achieved because when they have segregated the control and the data plane separately. So there will be switches connected to the pool of servers which handles the whole data, and there is an SDN controller where you do all the required network configuration through software. So this kind of software-defined networking is actually helping us to, or is actually helping to achieve the beneficial way, or in a larger way, it is actually isolating the application from the pool of application servers. So this kind of approach, if we implement in our automotive, that is called as software-defined vehicle. Or let's take this example, software-defined mobile industry, which is nothing but in your PC and in the smartphone industry. We have seen that software is in the form of application. It itself is creating an ecosystem which is completely decoupled from the hardware, and like this ecosystem is built once they decouple the hardware and the underlying software. So in mobile phones, we would have seen our hardwares like this. So there would be a display, there would be a like short range communications sensors like Zigbee, Bluetooth, and we'll have a CPU, memory, sensors, and we have network connectivity on top of this. These are the hardware. On top of this, we have drivers, board support package, and OS, dedicated operating system. On top of dedicated operating system, then we have some sort of middleware. Then on top of that, we have an application. This application now completely independent of the underlying hardware. So this kind of, I would say, layered but a service-oriented architecture would be implemented in automotive going forward. So which is nothing but your software-defined vehicle, or which is called as the software-defined vehicle. So in simple terms, decoupling of hardware from software and the introduction of software abstraction layer and the platform are the fundamental concepts. So basically, two things. One, you decouple the hardware from software. Other one is you introduce a software abstraction layer between the platforms. So these fundamental concept is what we have seen in various industries like telecom, PC, and smartphone. So now that can be applied to automotive industry also. So if you see, and I will not completely deny that automotive has not been transformed, or automotive software has not been transformed. In automotive also, they have invested a lot on classic AutoSAR models, where the idea was to segregate or decouple the hardware and software separately. So there the intention was not to come up with a solution for solving or with the idea of solving the on-the-air updates or updating the entire software. There the idea was to come up with a reusable software. So I'll talk a bit about the attempt that is made in automotive industry to isolate hardware and software also. So here, what do I mean by this software hardware decoupling? So software and hardware decoupling is nothing but where we have a layered arrangement of your hardware and then you have your components of system around the hardware and the software. Again, in that software, it can further classified into or arranged into driver and application. And in that driver, we will have an operating system, a middleware, and service-oriented architecture or a mechanism to then APIs, then cloud services. So this is what I mean by software and hardware decoupling. So moving from this to this is what we call it as SDV. So finally, we will have a cloud service platform, and we will have a onboard basic software and a onboard hardware. So the fundamental concepts in SDV is there is going to be a change in the vehicle EAD architecture, and that is happening. So with this, there would be a decoupling, and that's the core concept, as I told you. So based on this separation, further software architecture change will introduce some sort of flexibility. And if you see in the vehicle architecture in automotive is actually varying from a distributed architecture to a domain-oriented architecture to a zonal and central architecture. So it's evolving like this. So for example, today we are using a vehicle that has multiple ECUs which are interconnected with standard protocol mechanisms such as CAN, LIN, FlexRay, and there were multiple gateway ECUs which is helping to exchange data between each of them. So this architecture is distributed architecture. So going forward, we might be using, or going forward, we will be moving to a domain centralized EE architecture. In a domain centralized EE architecture, there would be a domain ECU which would be relatively better hardware configured ECU, or which has more, which is a more powerful ECU. In this way, multiple functionalities would be taken care by the domain ECU. And then going forward, we will have a vehicle centralized EE architecture where there will be zone computers depending on different arrangements in your vehicle, or your vehicle would be classified into multiple zones, and physically these zone oriented ECUs would be there, and which would be made of an high performance computer. There would be a high performance computing acting as a zone oriented ECU, and which is interacting with the cloud, and there might be a function or a model that is hosted in the cloud, and there might be a central kind of computation that will be happening in the cloud, and data exchange happening between your zone ECU and your cloud function. So going forward, we will be seeing an architecture from completely moving away from a distributed E&D architecture. So in this zonal computers or zone-based ECUs, HPC, it stands for high performance computer. So it is going to be the key element that enables the software defined vehicle. So without HPC, we cannot able to visualize the SDV. That is very, very, so we cannot able to visualize the SDV. So here on, I'll be using SDV, which denotes software defined. So HPC allows the execution of vehicle function of different domains on a powerful computing platform. So it makes it easier to upgrade the in-vehicle software. So with the advent of HPC, we will be executing multiple vehicle functions or multiple domain functions in one single platform. And this platform is a computing platform, but more powerful platform, which actually allows us easier to upgrade the in-vehicle software. That's the whole idea. So the use of HPC is to consolidate the software of different domains. So going forward, we might not have a separate ECU for body domain, chassis domain, something like that. So with the advent of HPC, we will be consolidating all those into one common high-performance machine, which we call it as a high-performance computer. And this is why the term a software-defined vehicle is coming. Why? Because your whole vehicle is based on that computer. Then we have zone controllers which are presented in the different physical regions of the vehicle and are connected via an Ethernet. So there are some lightweight protocols and there are some lightweight mechanisms like Ethernet with a simplified cabling and wiring operation is actually will be introduced when we are moving to the zonal architecture. So this is the ECU architecture that's what we will be seeing. Say for example, you have to read this like this, or you have to read this figure like this. There can be SLD system like your airbags, your engine management system, and other systems like which are real time as well as very high critical when it comes to safety. Then you might be having a SLB system like your brake lamps. Then you might be having a non-ASIL or ASIL-QM system like your infotainment systems. So see, we might be having a microcontroller based hardware. On top of that, where a classic AutoSAR stack or classic AutoSAR middleware is running with AutoSAR operating system. Then on top of that, a software application is running. This could be one use case, or this could be one ECU. Whereas there would be an SLB system which is purely based on microprocessor hardware, which is not controller hardware, which is purely based on processor and which is running some sort of POSIX OS. This POSIX OS can be a Linux or can be QNX, and on top of that, it's running a adaptive AutoSAR stack and adaptive AutoSAR application is running. Then we have HPC hardware, high performance hardware, where we see an hypervisor is there, which means you would have seen hypervisors which emulates the hardware into multiple hardware, a single hardware into multiple hardware. The best example that we have seen is the virtualization things that's happening. So if you have used some sort of virtualizer and virtualization tools, you would have experienced this where we are running a guest and host or multiple guest operating systems on one single host operating system. So on top of this hypervisor, we might have a POSIX OS container platform on which an app is running. Then on the same hypervisor, we might be having an Android Automotive stack that is running, that is interacting with the UI UX. So this could be a pure ASIL-QM or non-ASIL system. So all these three things would be interconnected via some sort of gateway ECUs, which might be exchanging values between CAN, LIN, FlexRay, or with Ethernet. So interestingly, we will have a very, very complex ecosystem where all form of software exists. You have your controller-based hardware, and you have your classic AutoSAR stack, and you will have a microprocessor-based hardware or an SoC where you will have your adaptive AutoSAR stack, and you will have a high-performance machine on top of high-performance machine. You'll have the hypervisor, and you'll have multiple containers that is running. So interestingly, we will be seeing all this shortly in one single vehicle. So the challenge with SDV is when we say SDV, we have to address a mixed latency system. So each of the domain issues now at the moment are independently driven, and they are following their own latencies. So they have, each of them are having their own different latency requirement. Accordingly, the hardware is chosen, and this is whole system is designed, and accordingly their software development life cycle is also managed. But going forward, when we talk about SDVs, so the SDVs will handle this mixed latency system by having a previous architecture, which I've like this kind of architecture will actually help or will be there in your SDV. So there will be a Ethernet protocol, which would be the backbone. So Ethernet allows you the service-oriented communication as used in the IT industries. So basically, with this, your PCs, your servers, mobile devices, enabling microservice architecture. Whereas if you see in automotive, we have not seen service-oriented architecture. Now only we are trying to migrate to service-oriented architecture, where earlier we were seeing only signal-oriented architecture, where deterministic signal like CAN, LIN, FlexRay are used for the real-time cases. So going forward, we will have both service-oriented architecture as well as signal-oriented architecture, because the SDV needs to fulfill safety and real-time requirement, but shall also provide flexibility of service-oriented software designs. Also, because we are talking about updates at all the levels. So now we will see different automotive embedded software architecture. I'm just giving a pass here. If you have any questions, if you have any comment or feedback, maybe you can please put it on the chat so that I can be able to address that. Is there any questions? Please feel free to post. I'll just pass for a minute. Please prepare and post your questions.
You can choose to unmute as well. Unmute and ask the questions.
Yeah, thanks for your question. We will take one by one. So can you please share with the with such huge changes on product services, how business model? I think before that I'll take the other question. Vivek is asking, using HPC with hypervisor would make the system undeterministic. Yes, do agreed. That is why we are not using those kind of things or those kind of HPC and hypervisor for SLD system. So when I say SLD, is where your deterministic real-time things comes into picture. So we are actually eliminating that, and we are moving towards, or we are not using, I would say we are not using hypervisor for such application. When you know that your application is purely deterministic or hard real-time, so in that case, we will not be using hypervisor. And can you please share such changes on the product services? Yes, there will be, because I don't think overnight all this will change. Going forward, yes, there will be a major change in the way the things getting updated, the way OEM is taking it, OEM adapting to it. So it slowly it will happen in terms of the business model. At the moment, we all have to wait and see. So what the next decade of SDV is throwing on us, to be frank. So nobody knows the clear business model, or nobody has laid down a very clear business model at the moment. Sagar is asking, can you explain hypervisor? So there are different types of hypervisor. I think they used to call type 1 hypervisor, type 2 hypervisor. Basically, hypervisor is a software that emulates your hardware, or that emulates and hardware kind of an environment. So what your like software will think, that it will think it is running on a pure software or like pure hardware, but it is running on a emulated hardware. Let's say, for example, you have a very large server farm, which could be a very high configured one single HPC, high performance computer. You may simply use an hypervisor to emulate, and you can create n number of entities or n number of emulated software virtual platforms. And on top of that, you may have containers, or you may have your guest operating system. So basically, this hypervisor, in short, you can assume it helps you to divide your high performance computing RAM and ROM. So if I have a PC today, I can install a virtual box, and I can install n number of operating systems, where all 3 operating systems are simultaneously running on my hypervisor. So you can go back and you can explore what is type 1 and type 2 hypervisors. Then do you mean ASIL D, ASIL B, ASIL QM all will run in one single hardware? No, I didn't mean that, Libin. So I said ASIL D alone, ASIL D, ASIL B, ASIL QM will exist as it exists today also. And what I showed in the slide, it doesn't mean that all these are running in same hardware. If you see, there is a microcontroller hardware, which means this is a separate ECU, which is a separate ASIL D system, and this is a separate hardware, but which is processor based. I mean to say, so in going forward, we will see an high performance computer based hardware, a processor based hardware, and a controller based hardware. We will see all these 3 kinds of hardware running software and coexisting. We will not, I'm not saying that we will be completely using only HPC, or we will be completely using only the processor based hardware, or I'm not saying we will be remaining or completely remaining with controller as we do now. So in today's market, if you are today's ecosystem, if you see, it's majority are microcontroller based, and for few applications, for few heavier applications, we are moving towards a bigger SoC. I hope I answered that question. So Satyajit is asking, so yeah, going forward, I'll explain what is service-oriented communication. So service-oriented communication and signal-oriented communication is different. If you have worked in classic AutoSAR, you know it purely follows a signal-oriented architecture, which means there is a predefined software stack which gets the data, and there will be a module for segregating that data. Then there will be a module for converting the PDU into actual data frame, and there will be a controller layer, there will be MCAL that drives. So everything is connected, everything is managed through some sort of handle IDs in your software. Whereas in the service-oriented architecture, we might be availing a service whenever it is needed. It would be there. So the interfaces are completely different. The code would be there, the module would be there. The upper layers would be availing that service whenever it is required. So there will not be any fixed flow of handles and data connections. So the architecture is plain simple. It's kind of only client and server based communication. Whenever there is a service request coming from the app will avail that service from the below layer. So Karthik, I think that's on service oriented architecture. What will be the career prospect in SDV? So it's a good question. So with this change in the ecosystem, going forward, we might need to have cross skills like AI, ML ops, then to work in purely if you want to work on application development, then you might require a different skill. Or if you want to work on this kind of industrialization, then obviously you require to have a DevOps. You might be having a ML ops skills, and then you might be required to have cloud related skills. This all will fall in one bucket. Or you might have core firmware OS skills, so which is again adaptive, which is following the service oriented architecture. And so to simply bring upon, in the previous decade, we have seen so much of electronic engineers entering into automotive. Going forward, we will see so many computer engineers and cloud and telecom oriented skill based members would be entering into automotive industry. So there will be a big change in the career prospect of the future automotive engineers, especially who are working on these kind of products. Hope I have answered all the questions. So let me continue. Now let me talk about different automotive embedded software architecture. There were in this whole PPT, like I have put down many different architecture. This is one default, I would say, skeleton, a default reference architecture. Nobody is proposing this. There on top of your electronics or on top of your ECU, there will be a middleware. There will be a library for doing advanced analytics. Then you will have your application. Your application will have connectivity with cloud platform, as well as your application will provide a very good user experience interface or a HMI. So this is what typically your software architecture should contain. So which is purely derived from mobile industry. And when it comes to implementation, still we will implement or we will follow our standard system engineering process through V development cycle. Or the vehicle architecture is further broken down into domain requirement architecture, then that is further broken down into like unit requirements, then feature requirements. And we will see the verification carried in the left arm, and we will see the like validation carried in the right arm. But certain portion will remain or will be completely converted into agile, in the agile way. Whereas the kind of unit implementation would be an iterative process. And here is an example. Let's take cars infotainment system, and we'll compare this with the actual architecture. I'm just taking this as an example product. So in your car, we have tuners, radio, multimedia, phone connectivity, telematics, navigation, then rear seat entertainment, and like voice recognition systems. We have all this. Now, if I put this across multiple layers, your hardware layer can contain or will be containing CPU and CPU related peripherals or a bootloader. On top of that, there might be an OS layer. On top of that, there might be an application and middleware layer. On top of that, you will have your touchscreen. So just to map various things. So in a typical infotainment system, now we see this layer is heavily dominant by CarPlay or Android. Android CarPlay or iOS. And here we are seeing a large community members developing the apps. And here the system, the front touch system, what we see. So for this kind of product, imagine that if you have a provision to achieve OTA, so that opens up, that gives a lot of flexibility for the users. And the whole from 2002, if you ask me, the whole. Any questions? the whole vehicle software ecosystem is actually moving towards building reusable assets. Initially, the OEMs were not focusing on that. They were trying to focus completely like a mechanical, solving their efficiency related problems. But then when they started having large amount of software and they spend a lot of money, they understand that the need for creating reusable assets. So they moved from customized software architecture to having a standardized piece of hardware, software, which can be reusable across multiple ECUs, and an application that can be customized based on the need, as well as it can be portable across multiple ECUs. So this application should be portable enough, and this stack should be reusable. This is the two things that they majorly focused in AutoSAR. And also on the basic side, the basic software side, they want to involve software that is coming from OEM and multiple vendors running in one single ECU. And that is something that's very well achieved with the classic AutoSAR stack. So the whole idea of AutoSAR is it's a consortium which is actively supporting the automotive market or automotive OEMs, tier ones, and this whole ecosystem for past 20 years. And they have been giving standards and standard tools and open architectures. And the key mantra for them is is nothing but cooperate on standards and compete on implementation. This is continuing and for past 20 years, and they have released several cut of open architecture for classic. And after 2017, they started introducing this adaptive architecture. So the classic AutoSAR architecture, I'll show you the both architecture. So these are the consortium members, where we have a bigger group of tier 1 GCC OEMs involved, and standard software vendor, tool vendors, and semicon vendors, all of them following and setting up the standard so that they solve their problems. They solve the common problems that they are facing. And in a large extent, because of this reusability, they reduce their products time to market. And what is the benefit each one is getting out of this? As a OEM, they are establishing, by following certain standards, they are establishing a development. It's like there is a standard development and distribution process, and they can able to compete on the innovative functions instead of recreating the same basic software again and again. They can focus more on the functionality, and they can simplify the software and system integration, and overall they can reduce the development cost. So this is what OEM is gaining. A supplier is reducing a lot of version divergence, and they don't want now they are building the software modules that can be reused across OEM. So it is very, very efficient for them, and they can make money with multiple customers. And also the increase application development efficiency. Overall, the supplier application efficiency, development efficiency is also increasing, and they are inventing a new business model. And tool providers, they are, for them it's a nice opportunity for them to build new tools that would be used in this ecosystem where the open standard is adopted. And new market entrant also will enable any new market entrant will get a new opportunity, new business model, where he is working like somewhere between OEM and supplier, or somewhere between supplier and tool provider. Or a new market entrant may focus only on skilling up all these members in ecosystem. So there is a potential opportunity for many members because of this. And the idea was to achieve interchangeability, exchangeability between supplier solution as a OEM, and exchangeability between vehicle platforms. All these have been achieved by classic AutoSAR. So if you ask me what is the difference between a legacy ECU and AutoSAR ECU, in legacy ECU, each function has its own system and microcontroller, whereas in AutoSAR ECU, certain functions became standardized. Then number of ECUs are growing very fastly, and here in AutoSAR, while moving towards AutoSAR ECU, still they standardized many specific interfaces that's used in the basic software, so they can able to contain certain things. And here hardware and software are very closely dependent in the legacy ECU, whereas hardware and software were made independent in AutoSAR ECU. I wouldn't say that they are completely decoupled. Still, there are a lot of things needs to be improved, because when they are defining the classic AutoSAR, the key idea in the mind was always the basic the end hardware would be a microcontroller. So it is, you see this whole system, the layered architecture is built or meant for a microcontroller. And software supplier is completely vendor dependent in legacy ECU, whereas in AutoSAR ECU, it is exchangeable and reusable. Now talking about classic AutoSAR layered architecture. In the classic AutoSAR layered architecture, we will have these 5 layers. There will be a runtime environment, there will be a service layer, there will be a ECU abstraction layer, there will be a MCAL layer. Finally, there will be a application layer. In simple sense, we are dividing basic software and the application software with the help of RT. This is what we call it as classic AutoSAR. Whereas in adaptive AutoSAR, there were multiple functional clusters. So this functional clusters is nothing but it is taken or it is utilized by an API or a service that is running on top of your or that is running on top of the application. So there will be an AutoSAR runtime or adaptive AutoSAR adaptive application layer. It's called as ERA. It's very similar to your RT. So this segregates your base software and your application. Then on top of your AutoSAR runtime ERA, your basic functional cluster services are availed by your application that is running in your ERA. We'll do a quick comparison, because in the earlier slide I told we are using a mix of processor and we will be using a mix of processor and controller based architecture when it comes to SDV. So how or what kind of systems will be still remain in classic, and what kind of system will move to adaptive? So if you see the classic systems like SLD systems such as airbags, ESP, engine management system, these will be running, will remain as a microcontroller based system mostly, and would be running classic AutoSAR stack. Whereas a processor based system would be running an adaptive AutoSAR stack. Then ECUs are connected via CAN, LIN, FlexRay, and whereas their ECUs are connected via Ethernet and communicate through some IP protocol. So some IP is a mechanism which gives you a scalable service-oriented middleware over IP. So some stands for service-oriented middleware. So if this is attained over IP, then that's called as some IP protocol. Most of the application on the old stack is written in C, whereas here the application are written in C++. So the stack, even the service-oriented architecture, is very well written in C++. So this is about the software architecture. Now let's try to understand something on the hypervisor. So this is how it will be, and hypervisor is running on an SoC or is running on an just any high performance computer, will allow you to run multiple guest operating systems A guest operating system can be an Android. A guest operating system can be a Linux OS. A guest OS can be a POSIX-based AutoSAR stack. So all these things would be running on one single SoC or a very powerful hardware. So this offering is taken from Open Synergy, where they are coming with an hypervisor called CoQoS, so which is functionally safe. So here, whatever that you see in the blue color, these are third-party application. Whatever that you see in orange, these blocks are coming from Open Synergy. Let's assume instead of Open Synergy, there might be a number of suppliers who offer this kind of hypervisors. Then there are other things which is integrated or modified by the supplier who supplies the hypervisor. Whatever that you see in the ash color is nothing but the hardware. So on a simple term, this Linux is assuming that it is running on hardware. Android is also assuming that it is running on a dedicated hardware. But actually, they both are running on one single hardware. For them, it is emulated to be a separate hardware, which is carried out by this hypervisor. Then, like on top of your hypervisor, we might run multiple containers. This container-based architecture is very, very popular in the cloud environment. A container is nothing but container technology is very well needed for OTA. OTA stands for on the air updates. A container technology is nothing but it contains software package that include your code and its dependency and libraries, tools, all settings that is required for runtime component. So let's say, for example, in many scenarios, we would have felt this as a developer. This code is running in my PC. It's not running in your PC. There might be a missing library. There might be a mismatch in the version of a library that you are using and that I am using as a developer. Most of the time, they would have seen this kind of practical issues. In that case, if we create a container and we run all the versions or all the required tools inside that container, it is super easy. So this kind of container-based apps would be running on these kind of machines. So it becomes very easy for us, which is lightweight, which is portable and secure space, basically. So this is really helpful when it comes to this as a big advantage when it comes to OTA. So then finally our OTA becomes a matter of copy paste and replacing certain container. So there are some containers that is existing in market like Docker, Podman, Kubernetes. So these things offer you or help you to do this containerize your own software. So with these are nothing but called as microservices. These are cloud related terms. If you are completely new, these are nothing but cloud related terms. With this kind of increasing use of microservice based communication in your vehicle backend, so there might be a lot of dependency on the APIs, or we might require several APIs to access various microservices that is available. So finally, we are doing all this to attain one big thing, which is nothing but OTA. Because in our classic way, we are not providing a standard approach to do software update. Whereas in this approach or in this way, there is a very clear provision, or there is a very clear idea for us to attain OTA. So there are the regular updates is available for critical as well as non-critical software. So OTA are two types. One is software over the air update. Other one is firmware over the air updates. So it's like you can either you can do both SOTA as well as FOTA with this OTA. Whereas now we are no way providing a room to do FOTA. With this kind of architectural changes, there will be a lot of seamless provision for doing photo. And what kind of updates that we will see in the vehicle software, because we are talking about many layers. So there might be an update happening on board support packages, drivers, because we are seeing all this kind of changes happening in our mobile phones. In our mobile phones, we are receiving periodic updates, not only for the apps that we are installing, we are getting firmware updates, we are getting OTA for our OS. So whenever a new OS is pushed, we are evolving that in our mobile phones. So we might receive updates for the hypervisors. We might get updates for the OS that is running, be it Android, be it ROS, or be it AutoSAR Classic. Then we have middleware components like JRE or ARA in Adaptive AutoSAR. Then on top of that, finally, we run different apps. And there are function-based OTAs also. So you can get safety updates, you can get updates for your drivers and controls, you can get updates for your infotainments. So now we have seen that we have adapted to a container-based system on which is driven with an hypervisor, where OTA is also possible. So what's next? If we have achieved all this, so your OEM will start functioning like a software company. One last piece is implementing or automating all this, which is nothing but DevOps. So DevOps is nothing but where we do some sort of continuous integration and continuous deployment. Since OTA is possible, the software deployment becomes a very easy piece. So the architecture for your vehicle, we will have these kind of things. So there will be a vehicle. So assume this is your vehicle. So it is running AutoSAR Classic, AutoSAR Adaptive, and some Android apps, and it has contained an hypervisor. Also, there is a board support package, bootloader. It has all the software components. And through some sort of cloud or some sort of edge services, it can access the backend. So in backend, there is a large set of standard feature which is actually helping us to do the continuous integration process and continuous deployment process. So in fact, we can, even while building, we can do virtual simulations. We can integrate, we can collaborate. So this opens up a large venue. So your wherever the functional safety required, even that can be engaged in the continuous integration process. And during this deployment process, your vehicle's automotive cyber security comes into the picture. So which is completely based on ISO 21434. So these basic principles are now incorporated in your DevOps cycle itself. So during development, I ensure that this piece of software require the functional standard according to ASIL D level, then accordingly ISO 262 standards are followed in the continuous integration process. So during the flash, if to attain the vehicle cyber security, we are following ISO 21434. So now, having said all this, there were multiple players in the market who are driving this to a very large extent. And one such member is active. IBM, Eclipse community is driving SDV in a very, very large way. So if you see the architecture which is proposed by IBM in a recent forum which they presented in year 2022, they come up with this kind of an architecture where there will be a vehicle hardware and there will be a private cloud which is posted by the OEM, and on top of that, Red Hat Linux is running with containers and microservices to communicate with cloud, as well as running the vehicle on hardware on the board. Then they have their Edge Application Manager, so where the Edge Application Manager is taking care of interaction between your in-vehicle infotainment system to the connected services. So this whole process, you can assume that it is running, it is hosted in the cloud, and this whole thing is hosted in the vehicle hardware, which is onboarded in your vehicle. So it is running some Android apps on top of a Java virtual manager, and this is a separate container. And there is other container which is running only the AI modules, and there is another container which is running the native code. So your in-vehicle infotainment system contains an SoC or a high-performance computer which is running an hypervisor that allows you to containerize these kind of things and run it as a multiple module. This is one architecture that is proposed and demonstrated by IBM, and this is other reference architecture when it comes to handle to a CI/CD workflow. Continuous integration will be rigorously followed during your development phase, whereas continuous deployment is a process that is followed during the end of the development phase. So how do you release the product, that is deployment, and how do you develop and how do you accommodate your changes is the continuous integration. So for one vehicle example, they attempted to do SIL and HIL based upon a cloud, handling large amount of data in CI/CD with CI/CD pipelines. So for that, they have proposed this architecture. And there were many interesting projects that is actually running. Maybe with this, I would like to summarize. I really urge you, if you are interested in SDV, I really urge you to explore all these projects. Eclipse alone is running on a Quixa, then OpenADX. I'll show some more videos also which I have. So these are offering certain standard products which can be helpful or which can be used in your SDVs. So similarly, AutoSAR is driving on a large way. You can be able to see the adaptive AutoSAR architecture open standards. So anybody who is completely new, maybe I'll show them how to use these documents. Let's say, for example, if you are completely new to AutoSAR, you don't know where to start, just go to autosar.org. So there they have a very clear bifurcation. So you can go for adaptive platform. Let's say if you want to study more about adaptive platform, pick the adaptive platform. Then you can pick whichsoever module that you want to understand. Let's say if I want to understand about their persistency module, if I go inside, I don't think they have given some. So let's say if I want to see log and trace. So usually it opens up. I don't know, now it is not opening up. It will give you the technical specification. If not, you can do a document search. So I'll show you. So you can do this document search. Here you can look for, let's say for adaptive platform, I'm looking only for explanatory documents. And if you do this and if you search, you will get all the explanatory document that is defined as part of adaptive architecture. And for the standard, let's say similarly you want to do for classic, you can pick this. So it will give you an explanatory document about for all the classic architecture. You can download the document and you can understand. So this is one way to start. Or you can also explore Eclipse SDV projects. So here Eclipse has hosted a lot of software-defined vehicle-based projects. We go into projects. Yeah, now the projects windows are loading. You will find many projects that is incubated by Eclipse, which is openly available, and For certain projects which is actually having a release also, you can explore that project. Say for example, LEDA is one combined ecosystem for SDV, and QXA, which is again based on the Eclipse SDV. So there you can explore these things. I will show one video. So I have two videos. I'll show one video how using Eclipse LEDA you can quickly prototype your ideas. So you can download, you can actually kickstart your SDV hands-on with any of these projects. Let's say if you go to Eclipse LEDA, they have given a proper documentation how to get start with Eclipse LEDA based tool, and how you can download a image that you can run on a QEmulator based device or on a Raspberry Pi, and how you can configure a device, and how you can use other tools, and how you can create your vehicle app, and how you can deploy. So they have given one such workflow approach for the simple hardware that we already have. So let me play this video. This is from Eclipse LEDA. I hope the audio is also available.
Jegan, unable to hear the audio.
1 minute. Maybe I will keep. How do I share the audio also? There is some means to share the audio.
In the share screen button, there is an option called Share a tab. It says it's better for videos and animation.
What is the tab then? Which is the tab that I need to select? Okay, to share. It will share a Chrome tab. Okay.
Oh, all right.
Okay, fine. Let me do that. I will open that still. Let it play from here itself.
You want to tinker around with automotive hardware, but need a software base for integrating your business logic? Would you like to evaluate the software-defined vehicle architecture and see how the software components integrate, but it's too difficult to find the basic building blocks for automotive? Wouldn't it be nice if you had a kind of playground where you could try out your ideas right away? Where you could focus entirely on the use cases instead of on setting up your own system? Well, good news! Such a playground exists. LEDA is an open collaboration platform for innovative automotive software development. LEDA comes as a pre-configured Linux distribution. Basic infrastructure services for cloud connectivity, application messaging, or accessing vehicle data are pre-installed. LEDA offers a container runtime for your containerized vehicle applications. You can fully customize it and build your own bootable images. Plus, you have the full update mechanism under your control, from device to cloud. LEDA is 100% open source, no registration, and no license fees. LEDA is your playground where you can instantly turn your ideas into reality. LEDA is easily extensible with your own containerized applications. And best of all, LEDA also runs on real hardware that is available to everyone. And because dreams should never remain just dreams, the Eclipse LEDA container runtime and vehicle abstraction layer will look and behave the same as in a real vehicle's computer. Build your ideas in the playground and make it automotive ready. Want to see how it works? Just try it out. Simply go to sdv.eclipse.org and get started.
Yeah, hope this is clear. Maybe I'll show other video to summarize what is SDV. Let me share other tab. So my screen is shared. So look at this. This is what active definition of
A software-defined vehicle is one whose features and functions are primarily enabled through software. Vehicle manufacturers used to differentiate themselves with mechanical features such as horsepower and torque. Today, consumers are increasingly looking for advanced features that can only be provided through software. Remember the transformation of cell phones? Originally, the software and hardware were tightly coupled, but with the introduction of the smartphone, the device became a platform capable of hosting a wide range of applications. A similar transformation is happening with vehicle software, enabling the continuous deployment and improvement of apps from multiple providers. The software-defined vehicle offers some unique advantages. In the past, upgrades required a trip to the dealership, or weren't even possible. With the software-defined vehicle, customers will be able to receive new features through over-the-air updates without ever leaving their home. Information will travel both ways, as manufacturers gain insight into every aspect of a vehicle's performance. OEMs and their partners will make several important shifts during this transition. Instead of a development cycle focused on model years, agile methodologies will drive continuous software development. Computing demands will also increase as vehicles process data from various sensors and even interact with other vehicles on the road. Security strategies will evolve to protect the whole system rather than simply protecting individual components. New business models and revenue streams will emerge, such as theft prevention services, emergency assistance alerts, and travel guides. In short, the software-defined vehicle will create opportunities for both consumers and OEMs, many of which have not even been conceived yet.
So this I end my presentation. So if you have any queries, we have 10 more minutes. I think we can discuss a debate. If you have any points, if you didn't understand anything. In current vehicle, Amit Singha is asking, in current vehicle, software updates happens through gateways, where gateways connect to the cloud and receive software update the individual ECU. Who will take the gateway work in SDV? So even in SDV, gateway ECUs will exist. So Vivek is asking which OEM is leading in SDV. I don't know which OEM is leading, but Volkswagen is attempting to build. They have built. It's not attempting. They have already built Volkswagen OS, which serves as a bigger middleware. And Volkswagen CEO in 2019 made a statement that going forward, our company would be completely a software-defined company. So I think Volkswagen and MBOS is also existing, which is from I think Mercedes. So all the companies, all the OEMs are into this. It's not who is driving it. All of them are participating in SDV. So in India, we see MBTEL Volkswagen Group is showcasing certain things, and typical tool vendors like Vector, Electrobit are also driving. Yes. Anybody? Any other questions? Thanks, Vivek. I could see somebody was raising their hand. If there are any questions, please feel free to unmute and ask, or please feel free to post it in chat. If you have no further questions, I think we can wind up.
Sure, Jegan.
Thanks, Kirtini.
Thank you, Jegan. I will just give it a couple more minutes and close the session. Thank you so much.
Sure.
Hi, everyone. I request everyone to take a couple of minutes to fill the feedback form. I've also shared our LinkedIn page link on the chat window. For any news or interesting updates about automotive industry and thought leadership articles, please give a follow.
So Dr. Shanti is asking, what is the job market of this? So if everybody starts adapting or moving towards the SDV, slowly this would be the trend, and this will open up many different job venues, starting from cloud to app development to firmware development, and to someone who is implementing the OTS. So it actually, automotive industry is way bigger than what all of us were thinking, and it is accommodating. So there will be a lot of job openings in ER&D companies, ER&D firms, and who are directly working with OEMs. It's anticipated to be like the next IT boom. So SDV has cybersecurity also. So very wide range of skills and job openings will open up in the market. It means mechanical engineer requires software knowledge. Then which one to be most important? I will not say mechanical engineer requires this sort of software knowledge. I mean to say where automotive companies and engineering firms who are working for automotive companies will hire members with these skill sets, members with cloud skill set, members with cybersecurity skill sets. So that's what I mean. But for a mechanical perspective, he can still remain as a application software developer, where let's say, for example, a mechanical engineer is required where he is developing an application for an engine management system. That is going to be there. The end application for your assembly system will be there, which would be supported, aided by instrumentation engineers, control engineers, mechanical engineers. Vivian is asking, internet is always active in this case. Yes, that's the assumption. Yes, internet is always there. Mahesh is asking, interesting presentation. Thanks, Mahesh. Do you have region-wise SDV progress details? I might not be having that. I think that's a very large research data. So I at the moment I don't have. Yes, Vivian, you are right. Without internet, it is like we are talking about software-defined something. Software-defined networks. Without having networks or without having internet, nothing will work. The same way, it's like the default assumption is internet is seamless. Internet is there. Thanks, Dr. Shanti. Please feel free to fill your feedback so that we can improvise next time if we have missed anything, or if anything that you feel that's to be added, covered, or if you are interested in any topic, you can highlight that in the feedback form also. It will work normal, then otherwise it will be risky. Yes. Thanks, Ganesh.
I think Jegan, we can start closing the session. I will give a couple minutes and end the session. Thank you so much.
Sure. Thanks everyone.
Thank you.